Welcome students to lecture 5, Electrophilic Aromatic Substitution. In this lecture we will study reactions of benzene and some of reactions of some of its substituents. So let us first try to understand benzene and substituted benzenes, their structures and aromaticity. So as we know, benzene is aromatic. If we substitute one hydrogen in benzene, we get substituted benzenes, that is from C6H6 we get C6H5X. This can give us, if you substitute the X with H, it gives us benzene itself, but if you substitute X with Cl, it gives you chlorobenzene, Br will give bromobenzene, OH will give phenol, NH2 will give aniline, SH will give thiophenol, CH3 substitution will give you methyl benzene, substitution by CHO will give you benzaldehyde, by carboxylic acid substitution will give you benzoic acid, substitution by NO2 will give you nitrobenzene, and substitution with CH2Cl will give you benzyl bromide, and substitution by NHCH3 will give you methyl aniline. So please take a look at these structures carefully and try to understand similarities and differences between them. The difference that we should pay more attention to is the difference between phenyl and benzyl groups. As shown here, phenyl group is a group which is C6H5, but the benzyl group instead is a C6H5 which is further attached to CH2. Therefore, we should distinguish these two groups and realize that phenyl is not equal to benzene. This will help us in understanding the structures of different compounds, including drug-like molecules. So further, this different substitution pattern tells us that different groups can either donate or withdraw electrons from the ring based on their electronegativity differences and ability to pull or donate lone pairs into the ring. This also is known to affect their aromaticity, but much work has not been done in this area, and there are some research opportunities in this field. So if you are interested, you can contact me after the class. So next we are moving to understand different reactions of benzene. Now, as we have studied in the last lecture, benzene undergoes substitution instead of the addition reactions. So reactions like halogenation, bromination, chlorination can be done on benzene by using a Lewis acid catalyst like ferric tribromide or ferric chloride along with Br2 and Cl2, and these will give us the corresponding bromobenzene and chlorobenzene compounds. But if you treat benzene with sulfuric acid, it will substitute the hydrogen with sulfonyl group. If you H2H2SO4, if you have HNO3 there, then it will hydrogen will be substituted by NO2, and reaction of benzene alkyl chloride in the presence of AlCl3 will give you alkyl benzene. Similarly, if you use acyl chloride, that is ROCl, Friedel-Crafts acylation takes place to give you acyl benzenes. In all these reactions, one common theme is that the benzene ring attacks the electrophile and displaces the hydrogen without proton. So we can now pay some attention to the mechanism of this substitution reaction. In this, you can see that the electrons in the pi cloud attack the electrophile because electrons have a negative charge and electrophile is positively charged, so they have attraction for each other, and depending on which center has the larger electron density within the ring, that will attack the electrophile. So there are three possibilities, as you can see, that once the electrophile attacks the ring, the positive charge of the electrophile is distributed within the ring, and the charge can be distributed at only three places, that is ortho, para, and ortho to the incoming electrophile. So therefore, we find that once the electrophile comes in, the ring gets a positive charge and the proton is displaced. That means it leaves the bonding pair behind, which forms this new double bond, and the proton goes into the medium. So this is to summarize, the aromatic ring attacks the electrophile and the proton is displaced. Electrons from the ring attack the positively charged electrophile. Intermediate with positive charge are formed, and then proton is lost to the medium to give the electrophile substituted benzenes. Note that the charge in the intermediate is distributed between only 3 carbon atoms, 2 of them are ortho and 1 is para. Generally, a mild base like alcohol or water is sufficient to take up this proton. Now, let us try to understand what is the effect of substitution on this electrophilic aromatics. Now, we have seen that monosubstitution of benzene gives only one product, but if you perform the electrophilic aromatic substitution on substituted benzenes, for example, toluene, which is methyl benzene, substitution can happen at multiple sites. So here you can see that the substituted benzene is R is CH3, it becomes toluene, and the electrons from the toluene will attack the electrophile. The charge will be distributed on the 3 carbon atoms, ortho, para, and ortho to the incoming electrophile, but this center is now meta to the electrophile. So depending on at which position the charge is stabilized, these attack will be favored. We see that for this ortho attack, the charge which is located at the ortho position to the electrophile, but it is directly attached to the methyl group. Therefore, methyl group can donate electrons by inductive effect and stabilize this charge. Therefore, this resonance structure is very stable, and therefore it will hasten the reaction, giving us the ortho substituted toluene. In case of the para attack, we find that 3 such other structures are possible where the incoming electrophile is instead of ortho, it is para to the methyl group. In this case, again one structure is possible in which the positive charge is on the carbon which is directly attached to the methyl group. Therefore, the methyl group is able to inductively donate electrons to the ring and stabilize the positive charge, giving a very stable intermediate. But in the other two resonance structures, such inductive electron donation is not possible from the methyl group, and therefore their relative stability is compared to that of the benzene intermediates coming from benzene. And once the proton is lost, it gives us the para substituted toluene. Similarly, for a meta attack, we find that 3 structures are possible from the attack of the meta carbon on the electrophile, which gives us positive charge at 3 centers on the ring, but none of them is directly stabilized by the methyl group by inductive effect. Therefore, the stability of these structures is low compared to structures like this one. Therefore, we find that only for the ortho and para attack, very stable structures for intermediates are possible. Thus, these stable intermediates are formed faster. Once they are formed faster, they will react faster to give the corresponding ortho and para substituted products. Only minor quantities of meta substituted products are formed because they are resulting in the intermediates are not very stable in comparison to the intermediates resulting from the ortho and para attack. Now, we can also compare the relative rates of different electrophilic aromatic substitution reactions. Here we see that benzene, if you try to sulfonate benzene using H2SO4, it takes about 30 minutes to complete this reaction. But instead of that, if you take toluene and treat it under similar conditions, it takes only 2 minutes and gives you the corresponding ortho and para substituted products as the major components. Meta substituted product is found only as minor component in the reaction. So therefore, we say that benzene is less reactive and toluene is more reactive than benzene because it takes significantly lesser time to react under similar conditions. Thus, in an electrophilic aromatic substitution reaction depends on the structure of the reactant, whether there are any substituents on the ring or not. The rate of the reaction and product ratio is also affected by this substitution. A group that increases the rate of the reaction compared to that of the benzene is called as activating group. For example, methyl activates the ring towards electrophilic aromatic substitution, therefore it is known as a activating group. Whereas other groups which decrease the rate of the electrophilic aromatic substitution compared to benzene are known as deactivating groups. Example being a nitro group. So we find that the nitrobenzene under sulfonation condition, although it gives us ortho and para products, this reaction is very slow compared to toluene and benzene. We can get a further understanding about relative reactivity of different compounds toward electrophilic aromatic substitution. For this, we will have to do competition experiments. In these experiments, two compounds like benzene and toluene or benzene and nitrobenzene are allowed to react with a limited amount of reagent. For example, if you perform nitration, the reaction flask in which you have already added toluene and benzene, that means both the compounds are present in the same flask, and then you add only one equivalent of the nitration mixture. This will lead to a competition between toluene and benzene for the nitrating reagent, and you find that nitrotoluene, which is formed from the nitration of toluene, is formed in larger amount than nitrobenzene, which is formed from the nitration of benzene. And the product ratio is 25:1. That means nitrotoluene is formed in large quantities from toluene comparison to the quantities of nitrobenzene formed from benzene. Similarly, when a mixture of benzene and chlorobenzene is nitrated, we find that nitrobenzene is the major product coming from benzene nitration, and the product chloronitrobenzene, which is formed by nitration of the chlorobenzene, is only formed as a minor product, and here the ratio is 30:1. Can you explain these facts given in point number 5 based on what we have learned earlier? This is your assignment question 3. Moving to the orientation of the electrophilic aromatic substitution and classification of these groups. From the mechanism that we have studied so far, we understood that in electrophilic aromatic substitution, a positive charge is developed in the intermediate. This positive charge is mostly localized at ring carbons that are ortho and para to the point of substitution. That means where the electrophile is adding. Any factor that stabilizes this intermediate by dispersing the positive charge will increase the rate of electrophilic aromatic substitution. For example, if you consider aniline, if electrophilic aromatic substitution is taking place on the ortho position of aniline, then the positive charge will be localized at these three centers, out of which this intermediate has carbon positively charged, which is directly attached to a amino group. That means the amino group can donate electrons through resonance effect and lead to a very stable intermediate. This group will stabilize the intermediate by dispersing the positive charge and increase the rate of the substitution. On the other hand, any factor that destabilizes the intermediate, it could do this by concentrating a positive charge in the ring, will decrease the rate of the reaction. For example, if you try to perform electrophilic aromatic substitution on nitrobenzene, then suppose if the electrophile is adding at the para position, then an intermediate will be formed in which the positive charge is on the carbon atom, which is directly attached to the nitro group, and this group is already electron withdrawing. That means it will further increase positive charge on this carbon, and it will lead to a very unstable intermediate, and therefore it will decrease the rate of the electrophilic aromatic substitution. A similar thing will happen if you have a carboxylic group, or if the substitution is taking place at the meta position of the nitro group, that this does not enhance the rate of the reaction, because none of these structures are very stabilizing. So based on this dispersal and stabilization of the positive charge that develops in the intermediate, we can classify the groups. Some groups which can donate electrons stabilize the intermediate and increase the rate of the reaction, therefore they are called as activating groups. Examples of such groups are the hydroxyl, amino, alkyl, ether and alkyl. So here are the examples that hydroxyl group, if you perform electrophilic aromatic substitution on phenol, then the intermediate will be stabilized by electron donation by the lone pairs on the oxygen atom, and substitution at the ortho and para position will be favored. Similar will be the case anilines and substituted aniline, and even for alkyl, as we have seen for the toluene, the alkyl groups by inductively donating electrons will stabilize the intermediate. So all these three groups are stabilizing the intermediate by resonance, electron donation through resonance. But this methyl group is stabilizing the intermediate through inductive electron donation. So on the other hand, though some groups withdraw electrons and destabilize the intermediate, and therefore they are known as deactivating. Such groups are nitro, carboxyl, carbonyl or halogen. So if you see carboxylic acid, carbonyl withdraw electron density by resonance or conjugation. That means they are withdrawing electron density through conjugation, and halogens like fluorine, chlorine, bromine withdraw electrons through inductive effect. So based on this, we can list some of the well-known activating and deactivating groups that are commonly seen in electrophilic aromatic substitution. So activating groups generally are ortho-para directing. Therefore, they are also known as ortho-para directing. So here are some of the examples. We have taken example of nitration of monosubstituted benzene. Therefore, there are three possibilities that you can form either the ortho, para or the meta product. But whenever a group is ortho, para directing or activating, it will lead to a formation of the ortho and para products as the major products, and only trace amounts of meta substituted compounds will be formed. When these aromatic rings are substituted by deactivating groups, we find that meta substituted products are formed. Based on the mechanism that we have studied earlier, can you explain why deactivating groups lead to meta products? So, for example, deactivating groups like nitro, trialkyl ammonium, cyanide, carboxylic acid, sulfonic acid, and aldehyde are all deactivating, and they lead to the formation of meta product as a major product in the reaction. And ortho and para products are found in only minor amounts. In the case of halogens, halogens are deactivating the ring towards electrophilic aromatic substitution, but they direct this substitution strangely to ortho and para position. Thus, we have to say that the halogens are deactivating but ortho para direct, and this can be understood by considering the fact that halogens deactivate by inductive electron withdrawal. This inductive electron withdrawal is because of their electronegativity. Because of this electron withdrawal, they will increase the positive charge on the intermediate and therefore lead to deactivation. All the halogens also have lone pairs of electrons on them, especially chlorine, bromine and iodine. Therefore, they will release some electron density by conjugation, and their conjugation with the ring of the lone pair. Therefore, they will act as ortho-para direct because they will stabilize the positive charge by mild electron donation through conjugation. So now we can summarize the substitution effect on electrophilic aromatic substitution. So the groups are mainly divided into two types, activating and deactivating. Most of the activating groups are ortho-para directors. Strongly activating groups, that is those will increase the rate of reaction significantly. These are amino, alkyl amino, OH group. Some other groups are moderately activating, that is they increase the rate of electrophilic aromatic substitution but only by a moderate amount. These are alkoxy, like the OCH3, OC2H5, etc. amide group, NHCOCH3, are also known as acetamide group. Then there are other groups which are weakly activating. That means they will activate the rings toward electrophilic aromatic substitution but by only a small amount. Examples of such groups are phenyl ring itself and alkyl groups like methyl, ethyl. In the case of activating group, in the case of deactivating groups, there are meta-direct, most of them are meta-direct like nitro, alkyl ammonium, trialkyl ammonium, cyanide, carboxylic acid, carbonyl compounds, sulfonic acid, aldehydes and ketones. Only the halogens are exception in that although they are ortho-para directors, they are deactivating. Can you use all this information to predict the products in the following reactions? Can you predict what will be the product of nitration of benzene, and that product is then brominated, what will be the final product? And when benzene is brominated, you will get one product. What is that product? And this product, when it is further nitrated, what will be the final end product? So please try to solve these problems and we will discuss them further in the class. So our next lecture will be on the electrophilic aromatic substitution in disubstituted benzenes and the applications of electrophilic aromatic substitution. So see you next week. Thank you.